is Alexander Lee, and I am the Vice President of the Association for Computing Machinery at Los Rios. The ACM is the world's largest educational and scientific computing society, delivering resources that advance computing as a science and as a profession. The ACM provides the computing field's premier digital library and serves its members and the computing profession with leading-edge publications, conferences, and career resources. Ooh. Today, we'll look at Laplace Expansion, and we'll see how it affects cryptography and ciphertext algorithms in C++. Here's an overview of our organization. The Laplace expansion is what we'll cover first. Then we'll look at its algorithmic design. We'll then do a walkthrough of our code. After we do our walkthrough, we'll do a runtime analysis where we look at its complexity. We'll look at ways we can optimize the code that we have at hand. We'll hand execute what we have. And then we'll conclude by talking about applications for different ciphers and further applications of matrices in computing. We'll then look at our team, and we'll look at future ACM chapter events. Here we have the Laplace expansion theorem. In front of you, it says that the determinant of a matrix is equal to the summation from j equals 1 to n of -1 raised to the ith row in j column of a matrix, where A is the corresponding matrix array element, and m sub I for the row and j for the column is its corresponding cofactor. So, wow, that was a lot, right? So I can simplify it as such. If you imagine just a small 3 by 3 array, right? In the first left-hand side, you'll see it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I say A sub 1, 1, it's not A11, it's 1, 1. You'll look at the number 1 in the 3 by 3 matrix, where you have 1, 2, 3, 4, 5, 6, 7, 8, 9. It's simply the first element in the first row in the first column, right here, 1. And the minor of it, to find the minor of it, I simply eliminate the first row and the first column, like here, and I get the mirror 5, 6, 8, 9. Then the theorem tells me to go and find the determinant of the matrix. I do that simply by crossing 5 and 9. I multiply that to get 45, and I subtract it from 6 times 8, and the result is -3. So the same process happens for the second minor right here, where we go over and we go down. We eliminate this column and this row, the same row, and we get -6. And we do the same thing for the last one right here. So I'm not going to spend more time on this because I plan to do it all over again in Python for the next part of this video series, part 2. But simply for our purposes here today, where we'll be applying this theorem, the Laplace expansion theorem, to encryption using a Hill cipher, I just wanted to show you the possibilities that you can achieve using this theorem. So here we have a 3 by 3 array. Imagine that you will apply matrix multiplication with a digraph or a vector to scramble a string, which we'll get into momentarily. But then imagine that you can arbitrarily define an n by n matrix. The complexity here is significantly larger than a 3 by 3 matrix. And understanding how to do this type of expansion can really be quite powerful if you need to compute the determinant of an n by n matrix algorithmically, and then multiply that and use that to encrypt a message. Your encryption would be pretty solid. It'd be incredibly difficult if you don't know how to work this right. It'd be incredibly difficult to decode it. Since our ACM chapter is viewing The Imitation Game, a movie featuring Alan Turing decoding Enigma during World War II, I figured it'd be appropriate to talk about encryption. But I'll continue what we were talking about with the Laplace expansion. After we have the determinants of our mirrors, we then define the cofactor of the element A as follows here, where we take negative I raised to the power of our row I plus our j column times the determinant of the corresponding element in the matrix. We'll note that if we do this, we raise negative 1 to the I plus j, we'll achieve a checkerboard pattern here, where you have an alternating sign pattern between positive and negative values for each row and column. This will make sense to you as we see the code. So here we take a closer look. You can start to see that it gets very hairy, very complicated. There's a lot of math involved, lots of linear algebra, but since my population here is mostly community college students, I want to just keep it simple and accessible. I will definitely go into the mathematical complexity in a later video if you're interested. So here's what we want to focus on today. We will be using the Laplace Expansion theorem to rework the Hill Cipher encryption. The traditional Hill Cipher creates this alphanumeric assignment where you can imagine these are characters, right? If you're starting to code this, these are characters in an array, and you have 27 elements. I have this space here if you want to have a message with a space. So I, instead of doing mod 26 later, I do mod 27, but you can see that this is going to correspond with the first index of the array and so forth. Let's define some terms now. So if we have a message called Turing, T-U-R-I-N-G, a digraph then is a term that this cipher will use. A digraph is a set of 2 consecutive letters in the string. So I pass through the message Turing, and I take out TU in the first pass to be the digraph, the set of 2 consecutive letters. Using then this array, I then codify T to be 19 here, and U to be 20 here. Then I multiply by a key. In my algorithm later on, you'll see that I randomly generate the key, but for demonstration purposes, we'll say that the generated key is 1734. Whenever we have a 1 by 2 matrix like this, we refer to it as a vector. It's not a C++ vector in the standard library, it's simply just a vector. We're still in the world of math here. To then apply the Hill Cipher, we'll use matrix multiplication. To do that, we'll take the first element 1, and we'll multiply it by the first element in the row here, 19. And then we'll take the second element here, 7, and then we'll multiply it by the second element here, 20. We'll repeat these steps by taking 3 times 19 here, plus 4 times 20 here. Our result is 159 on top, and 137 on bottom. The next step in the Hill Cipher is to apply the modulo operator. We'll apply the modulus to 159 to get 24, and 137 to get 2. The resulting encrypted digraph gives us 24 and 2, which if we look, gives us Y and C, which is a resulting digraph for the ciphertext. So we'll say their string ciphertext will equal this, and then increment through the loop and increment our iterator. You'll see that the same exact thing happens for our second pass and our third pass. After we achieve, after we pass through our loop sufficiently, we'll see that our algorithm detects the null string character and then breaks. Our ciphertext at this point is YCTCBJ. Now, if I want to apply the Laplace expansion, and I'll save this for part 2 while I do this entirely in Python, I'll generate a 5 by 5 matrix, and I know I can generate an n by n matrix, but for simplicity and just for demonstration purposes, I'll keep it to a 5 by 5. This matrix is then our key here. Our key will multiply with our scalar, with our vector, which is going to be our digraph, or even our trigraph, depending on our arrays. Our key is going to be what we multiply our digraph here, or it can be our trigraph. We can use 3 letters, but let's go by 2. So our digraph, So if we have a very large key, you can imagine that it scrambles the characters quite significantly more, right? We'll then find cofactors and minors, and then we'll determine determinants. Then we'll multiply the determinants with the key again to scramble the key with each pass. So you will imagine that it's a distinct encryption then for each individual digraph. So it's not just the same key for each digraph. You'll have to reorient it or reshift your key and multiply back if you want to decrypt your message. This will definitely add an additional layer of encryption to the cipher. Here's a proof. So now that I've shown you essentially what a Hill cipher is and what Laplace expansion theorem is, I wanted to just show you the proof of the theorem, since no one should take a giant equation on the basis that it's a giant complicated looking equation without some form of proof that it actually is true. We want to start by showing that the cofactor expansion along the jth column will produce the same result as the cofactor expansion along the first column. So we observe that the column j can be shifted into the first position by j minus 1 consecutive row switches. So let A prime equal the A prime of the first element from the matrix performed by the necessary column switches. So if you're confused what that all means, don't worry, I'm on the same boat as you. I've spent a month on this project, so let me explain. If I go back, you'll see that this is the first element, the second element, and so on in the row, right? So what we essentially do, wait, let me double check. Just kidding. What we essentially do is we shift these crosshairs right over, and we eliminate down and to the right. So here, down and to the right, and the minor's here, and here, down to the right. This will be our minor. And over here, it shifts again, this will be our minor. And so again, you can imagine that as n gets larger, not only will the complexity of this algorithm increase, but increase towards n to the n, but your level of encryption then for the message will be quite significant, right? So just think about that. Think about what you would want to encrypt. So password sensitive information, right? But here's the proof. The determinant, we set that equal to -1 to the j minus 1 times the determinant of A prime. Then I don't want to lose anyone, but we essentially prove that the summation is equal to what we started with, which is this. So this is an algorithms talk. I just wanted to preface the mathematical basis for it. So I'll be moving on now into our code. So here's the algorithm, okay? We take in the secret message, then we randomly generate a seeded key at runtime. Then 3, we encode using the generated key. And 4, we output the ciphertext to console. So now let's look at the code. So here I have my code for the Laplace expansion and encryption, where we implement Hill Cipher. Let's just run it. So it generates this key here, and I've seeded it at runtime, so if I run it again, it will generate a new key every single time. See? So then it prompts me for my message, and seeing that our chapter will view the imitation game again this coming Friday at 8, it's only fitting that we fit our theme of cryptography and call the message, or the plaintext, Turing, for Alan Turing. After it goes through my algorithm, the resulting ciphertext string is shown here. So how the heck did this happen? Well, if you recall the brief mathematical talk I gave in the beginning part of this video, you'll see that I outlaid what Laplace expansion is and how to perform Laplace expansion. On the various method forward declarations here, I forward declare my methods just so I can put them below for readability. So I have my modulus inverse here, my cofactor method here, my determinant, my adjoint, and my regular inverse here for the sign map. I use vectors because they're dynamically allocated, and that helps make my program more efficient in terms of memory space. It also is why I really enjoy programming in C++, but the next part of this bootcamp will be in Python. With C++, you have a lot of control over the precise memory allocament of even the bitwise operations of your program. And I think with that level of control, you can really create the most efficient programs in the world. So let's look at how everything actually works. So after we get our plaintext, after it's c'd, I declare a temp equal to n minus plaintext.size. So this function here, this library function, gets the size of whatever my message is from console that the user types in. It then performs modulo arithmetic by the size of the key matrix, in this case n. And we define n up here to be 2. We do this again a second time, just so that we have digraphs. I then parse through the message to convert it to numbers using our alphanumeric key, and then I delimit it by each character with a null space here, an underscore. Then I use our k value, and I mean mathematical constant here, not programming constant. This will change, so just to relieve some confusion, I'll just say k. We'll process each array index, then we'll declare a string to hold our ciphertext, and then we have a while loop here with an embedded for loop. While our constant k is less than the size of our plaintext string, we loop through our digraphs, set the initial summation at 0, then have our cofactor k here, right? Yes. Then we perform the matrix multiplication with our key and parse digraphs, meaning that each digraph has been separated. The string turing has been separated into the digraphs tu, ri, and ng. Then I apply matrix multiplication, which you saw earlier in the mathematical preface, where I multiply each element in the key by the plaintext vector, and then I apply the modulo operator to my result until we get the resulting string here. I do this more than once simply because I'm so sorry. I actually do this 4 times because I do it in a very efficient way. Instead of doing the multiplication, then addition, then modulo, I do it all in one step, and so it iterates through this operation very fast. So I have to catch at each interval it does it. So I apply the modulo operator here, 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 and here. And if you think about it, there are elements here, 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 and here. So in each case that it's applied to the plaintext, I have to perform the modulo, or else it won't work and won't encode my message correctly. So I made sure to debug this program and make sure that it actually works and that the logic is sound, and that took me considerable time. My next video will not take this long, hopefully, but I thought it was very cool, and it gave me the opportunity to learn a lot while I was making this project. So I wanted to really share what I've created with everyone, and I hope that you enjoyed what I brought to life, really. We then convert back our digraph into characters here because in this step is still numeric. Then I refresh my constant k for the next pass by setting it back to the dimensions of the key so that it multiplies correctly and implements the matrix multiplication correctly. At this stage, the pass is now complete. At this stage, the pass is now complete, and the message is successfully encrypted. We finally display the result with visual flair. We type it out, and then we have the result is the cipher string. If you want more information, I'll leave this program up on the video link so you can look at it yourself and play around with it. I've also left a lot of references here: polygraphic substitution ciphers, stuff from the NSA, the crypto sculpture where the cipher is encoded, code busters from Science Olympiad. Here's a look at part 2, which I don't know if I will get to. And here's the ASCII table that you can use for reference that I used later on because I wanted to go more than 27 characters. But that concludes the first part 1 of this bootcamp. I really meant it to be a proof of concept. There is a lot of room for improvement, and certainly this code is not perfect, can be definitely more improved. So I hope you enjoyed it. This is just an undergraduate student's take on cryptography using a linear algebra theorem. Laplace expansion is a theorem from linear algebra. And I hope you take it and it inspires you to go do something really cool. And I hope you learn from that too. Cheers. So, now I just want to talk about our team. So Esther Cheng is our Women in Data Science ambassador, and she's our webmaster. So she's helping us work with all our PHP, CSS, and JavaScript. And I'm the vice president of the ACM. So if our president's sick, I guess I have to put on my hat and become the person in charge. And then Ishan's our president. He's the person in charge. So, just kidding on the side, we're really just a team of undergraduate students here. And we really put on different hats, actually. So sometimes I work with Esther and I help add in different polyfills to our website. Or I add on different text elements or visual elements. And Esther sometimes helps us with paperwork and conferences, and Ishan sometimes, we do leak code together every now and then, and we kind of try to help each other become better, and I think that's really what a team does. I'm really grateful to be working with these people. Our upcoming events, so we plan to have this movie night last Friday, but it looks like we're going to have it again this coming Friday. We'll have a book club that recurs every Thursday at 7, where we just read an excerpt from this book. Our Discord account is linked there, and you can scan the reoccurring QR codes on each flyer to get access to our link tree while our new website is being built dynamically using JavaScript. We have coding challenges every Tuesday at noon. So we'll post a very, very easy problem, and we'll try to get the most efficient solution for it, and we'll really analyze why it's so efficient. We'll do this every day on our server at Tuesday. I'm sorry, not every day, every Tuesday on our server at noon. I'd like to take a moment now and recognize the Indigenous Peoples Week, especially the Navajo code breakers and for their service during World War II. I have here the Los Rios Community College District's Indigenous Land Acknowledgement Statement, and I'll read it in full. In the spirit of community and social justice, we acknowledge the land on which our 4 colleges reside as the traditional homelands of the Nisean, Maidu, and Miwok tribal nations. These sovereign people have been the caretakers of the health of the rivers, the wildlife, the plant life, and the overall eco-social balance in the greater Sacramento region since time immemorial. Despite centuries of genocide and occupation, the Nicaean, Maidu, and Miwok continue as vibrant and resilient tribes and bands, both federally recognized and unrecognized. Tribal citizens of these nations continue to be an active and important part of our Los Rios community. We take this opportunity to acknowledge the land and our responsibility to the original peoples, the present-day Nicaean, Maidu, and Miwok tribal nations. And here's our QR code again. So just scan it and you'll get access to all our upcoming events. Thank you for watching. It's been a pleasure to record this video, to edit this video, to make the code, to do the project. It's been a working project of mine for about a month. It's difficult juggling a lot of classes while doing this, so I appreciate your time. Thanks. Bye-bye.